Right, hello grade 12s. This is the beginning of the grade 12 probability section. Specifically, it refers to it's what we refer to as the counting principle. Now, this does make it a little bit difficult, the whole idea that we're going to call it the counting principle, but mostly when we think about counting, we think about adding. But the operations we are generally going to be following here is not addition, it's going to be multiplication. So why would we call it the counting principle if we're going to be using lots and lots and lots of multiplication? Well, basically, what we're doing here is we are trying to count the number of different ways in which something can happen, because that is the very definition of probability. So the whole idea here is the following. Let's just quickly get sidetracked a little bit. Okay. If you look at the definition of probability, the definition of probability says the probability of an event A happening is equal to the number of ways in which that event A can happen, divided by the number of ways in which everything in that sample space can happen. So if you think back about like grade 8 or grade 9, when we were talking about you throw a die and you want to know what's the probability of getting an even number on a die, then pretty much what you did was you said, okay, first things first, if A is an even number, then we have to go and understand that A could potentially be the number 2, the number 4, or the number 6 on a die. So these are the number of ways that I can get an even number on a die. There are actually then 3 ways in which this can happen. So there are 3 ways in which event A can happen. Whereas the number of ways that pretty much any event can happen in the sample space is going to be 6. Because you think about it, then you realize on a die, if it's a 6-sided die, you can then go and throw 1, 2, 3, 4, 5, and 6, which means the number of ways how things in the sample space can happen is equal to 6. And that is why the probability of throwing an even number on a die is 3 out of 6 or 1 out of 2. So this is why we are doing this topic called the counting principle, because we need to be able to count in how many different ways can an event A happen, and then we need to count in how many different ways can all the events in the sample space happen. So that's the goal behind the counting principle, is counting or finding a calculation for getting that number of ways that event happens and the number of ways everything in the sample space can happen. So that's the goal here. Okay, right. So let's look at a straightforward example, just so we can feel our way forward. If 3 people run a race, in how many different ways can the gold, silver, and bronze medals be allocated? Now, initially when you do this problem, we're going to do it the long way around, just so you can understand the shortcuts we're going to be using later. So let's go and say, I'm not going to be very creative, let's just say the people running the race, we have athlete A, we have athlete B, and we have athlete C running the race. Those are the 3 people running the race. So if you think about it, first things first, we have to award a gold medal. So awarding the gold medal means we have 3 options in awarding the gold medal. The gold medal could go to athlete A, the gold medal could go to athlete B, or the gold medal could go to athlete C. Now, if athlete A is first to cross the line and gets the gold medal, then athlete A is no longer available for the second event, which is the silver medal. So if A wins gold, then only B or C could win the silver. Or, over here, if B crosses the line first, so B wins gold, then only A or C are available for the silver medal. If C crosses the line first and wins gold, then over here, only A or B are available for that silver medal. And then if we keep going, we realize if A wins, B comes second, then only C can come third. If A wins, C comes second, then only B can come third. If B won, A came second, then C has to come third. If B won and C came second, A needs to come third. If C won and A came second, B needs to come third. And if C won and B came second, then A came third. So what we've done now, what we've established here, is we've established and this is the counting part, we've established there's 1, 2, 3, 4, 5, 6 different ways in which this race could have ended. So I literally have listed here the 6 different outcomes of this race. But you can imagine, for instance, if you had 10 athletes running a race, and now suddenly you don't just want to know who got gold, silver, and bronze. You want to actually know who came first, second, third, fourth, fifth. Then you can imagine that this tree diagram is going to be insane to draw. You're not going to be able to draw that tree diagram. It's just going to be way, way, way too much. But what we need to pick up here is we need to pick up that generally what happened here is the following. We had 3 choices on the first one, so I'm going to write that down. 3 people to award the gold medal to. On the second event, because we'd already picked the first person, we only were left with 2 people over there to win the silver. And then the moment we picked that second person to win silver, we were actually only left each time with only 1 person at the end to win the bronze. And if you look at it, you realize it's 3 by 2 by 1. And if I multiply that 3 by 2 by 1, I end up with 6, which is exactly the number of outcomes that I had in this event. And this is why I'm saying it's called the counting principle, because you're counting the number of ways in which something can happen. But technically speaking, you are not actually adding, because we always think of counting as adding. We're going to be multiplying. Okay, so we're going to be multiplying to find the number of ways in which something can happen. Okay, so that's just the idea behind it, this multiplication. Okay, right, now the next thing we have to talk about, a certain notation in mathematics. And that notation is called factorial notation. Factorial notation. So if I go and I write any number with an exclamation mark next to it, that is actually not an exclamation mark in mathematics. That is what we call factorial notation. Okay, so it's not in, no, it's in factorial. Now I'll talk just now about what the definition is of n factorial. But I first want to do an example, because if I just show you practically what it means, it actually becomes a lot easier. So if I say 5 factorial, and by the way, it is on your calculator, that factorial button. It's right over there. So if you have this button x to the power of -1, just above it there. I don't know if you can see that actually. Let me try and see if I can get that closer to the camera. There we go. That's better. So just above that x to the power of -1, you have that x factorial. So because you've got that x factorial, you can actually use your calculator. So even though we have no idea currently about how to get it, I can go and I can say 5, and then I have to press shift and that factorial button. Oh, let me just switch it on. 5 factorial equal to. And they tell me it's equal to 120. So I'm going to write this down over here. But now to understand how they got to 120, we need to understand how this factorial notation works. So factorial notation takes the number that's given there, the number 5, and then it kind of clicks over, but it clicks in a descending order, and it only clicks on positive integers. So please understand, factorial notation only works with positive integers in a descending order, meaning takes 5, so the next positive integer in a descending order is 4, so multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1, and when it hits 1 it stops, because obviously we're now out of positive integers, so I have to stop. And if you go and you just do that manually, you'll see 5 times 4 times 3 times 2 times 1 is equal to 120. And that's what factorial notation means. So the very formal definition of factorial notation pretty much says, start with this number, whatever it might be, n, and then you multiply that by one number down, so n minus 1. And then you multiply that by one number down, so n minus 2. And then you multiply that by one number down, so n minus 3. And you keep on going until you hit 1. Because the moment you hit 1, you have to stop, because, careful, if you were to go and multiply by 0 there, then the whole thing just becomes 0. Okay, and that's actually something we need to talk about. They had to, for a lot of reasons, we're not necessarily going to get into it, they had to go and they had to define what 0 factorial means. Okay, because technically speaking, we never go further than 1, we just multiply there. But there is a reason for this. They defined, and this is a definition, so it's something you can learn. You can also use a calculator to help you. 0 factorial was defined as 1. Okay, for a very specific reason. I know you go like, that doesn't make any sense. It's something you can just learn. Like with exponents where you know a negative exponent means it's on the wrong side of the line. Or with exponents where you know anything to the power of 0 is always equal to 1. Same thing here, 0 factorial always equal to 1. So please remember that. So let's see how this factorial notation actually make these problems a lot easier to do than what we had to do over here with the runners, where we had to go and write out the entire tree diagram to look at all the possible options. Okay. So in this problem it says, there are 8 swimmers swimming in a race. In how many ways can you allocate the lanes if there are 8 lanes available? So pretty much what we're saying is there's a swimming pool, there's only 8 lanes, so you have lane 1, 2, 3, 4, 5, all the way to 8, and there are going to be 8 swimmers swimming in those lanes. So if you think about it, then you realize this is very much like the first problem with the runners. I have 8 available choices. So I have 8 people standing there next to the side of the swimming pool. So the first lane, I can put any one of those 8 people in there. So I have 8 options to put into the first lane. But the moment I've allocated a person to the first lane, when I get to the second lane, I no longer have 8 options available. I now only have 7 options available. And when I get to the next lane, I now no longer have 7 options available. I have 6 options available. So you get the idea of that factorial notation where we say it's going to be 8 people possible in the first lane. So if you had to draw a tree diagram, there's going to be 8 options. But then after I've allocated the first lane, that swimmer is no longer available. So that means in the next lane, I can only put 7. So you can imagine there's 8 by 7 by 6 by 5 by 4. And factorial notation just makes this a lot easier to do. So all I'm going to do here is I'm going to say, yes, it is 8 times 7 times 6 times 5 times 4, but it's much easier just to go and say 8 factorial and put that into my calculator. So 8 shift factorial equals, and that gives me, believe it or not, 40,320 different ways in which you can allocate these 8 swimmers into 8 lanes of a swimming pool. I know, the first time you see this, you go like, no, it can't be that many. But it gets really big, really, really quickly. So a lot of these counting that we're going to be doing are these massive numbers. And that's why it's a good idea not to draw the tree diagram to figure it out, but to understand the whole multiplication in order to count, number one, and also using factorial notation to our advantage because it just shortens the process quite nicely. So that's 40,320 different ways in which I can allocate these 8 swimmers into 8 lanes. Okay, right. Now, sometimes, and this is pretty much what this little section is about. I know it sounds very fancy. It says choosing R elements out of a sample space with N elements. Let me maybe just do this so you can see what I'm talking about here. So pretty much what happens here is we're not always going to use all of the elements available. A good example was the runners in that race. If you think about the runners in the race, you hardly ever get a race with 3 runners. You would normally get at least like 10 runners in a race. So if I had to go and say, instead of just allocating gold, silver, and bronze to these 3 runners, how many ways can I allocate it if there are 10 runners, but I'm not interested in all 10 positions? I'm just interested in the first 3 positions. Okay. In this one, I've adjusted the swimming one. It says there are 8 lanes available at a swimming pool. So that means we have 8 places to allocate. In how many ways can lanes be allocated if there are 11 swimmers? Now, what you need to understand here is you need to understand, in the first lane, I have 11 choices because there are 11 people. I can choose any of those 11 people. So definitely there are 11 people for the first lane. So if I quickly had to go and just say there's the first lane, second, and I just list them like that so you can see what I'm busy doing. So there are my 8 lanes that I have to allocate. So there are 11 people I can put into the first lane. Second lane, because I've already picked one, there are now only 10 people available there. Then 9, then 8, then 7, then 6, then 5, then 4. And then I have to stop. I have to stop there because I have no more lanes to allocate. But, like we did previously with this example, I can then just go and multiply. Okay, so we're still multiplying, but we have to realize, because we have too many elements to allocate in these available spaces, I am going to stop before I reach one. So sometimes factorial notation is not enough, because factorial notation will always run all the way to 1. It will only stop when it gets to 1. Whereas this particular one needs to stop at 4 because I've run out of space. So you can actually go and you can type this into your calculator. It'll take a little while, but you can type it in. So 11. And please remember to stop at the right space. Stop at 4. So that's going to be quite big, 6,652,800. Let's just write that down. And again, people, you're going to have to get used to these massive numbers, because a lot of the time we tend to think we did something wrong because the number is so big, but generally they are really, really, really this big. Okay, so you can definitely do it like this. This is the manual way of doing it. So please just remember that you can't just use factorial notation if you have more elements to allocate into less spaces. That's what this says. Choosing R elements out of a sample space within elements. Now there is a shorter way to do this. There's a shorter way to do this, and that is to understand something called a permutation. Fancy word, I know. You don't really even have to remember this name. Generally, they don't talk about this in the textbooks. A permutation. So a permutation is written in permutation R. So that's where that in and that R comes from. So in is all the available elements in the sample space. Whereas R is the number of these elements in the sample space you're going to be choosing. So R is the number of elements chosen. And I did show this to you up here at the top where I say you're choosing R elements out of a sample space within elements. So that's exactly what this is. This is the one where you say, for instance, in my example, in then will be equal to 11 because we had 11 people available. But R is then equal to 8 simply because we only had 8 lanes, so we can only choose 8 of the 11 swimmers. Now, just quickly to show you, by the way, there's a calculator button for this in permutation R. So let me show you that to you first before I discuss what this means. The calculator button, interestingly enough, is just above the multiplication button, which should technically speaking be where we find it because that's what we're doing, we're multiplying. So you'll see this little button there, I hope you can see it there, just above the multiplication, there's my in permutation R. So I can type in 11, because that's how many available choices I have, shift, and I type the permutation button, and then 8, because that's how many I'm choosing, and if I press equal, look what I've got, match that. 6,652,800, which is exactly what I got doing this manually. So I can immediately just go and say 11 permutation 8 is equal to that 6,652,800. There we go. Now, just for interest's sake, you don't need to know this at all. You can just use the calculator button. There's a formula for permutations to explain why this actually works. And that formula says it's in factorial over n minus r factorial. Again, this formula is not on your formula sheet and you don't need to know it at all. You can just use the calculator. But for interest's sake, if I go and I look at that 11 permutation 8 again and the formula, then what we've got is we've got 11 factorial over here. This is just showing you how it works. Over 11 minus 8 factorial. So pretty much 11 factorial is then equal to 11 times 10 times 9 times 8 times, I'm going to skip a few, and I'm going to go times 5, 4, 3, 2, and 1. Whereas at the bottom, 11 minus 8 is 3. So 11 minus 8 is 3 factorial. So if you think about 3 factorial, I have this. It's 3 times 2 times 1. Which, if you do a little bit of cancellation here, saying I can divide 3 into 3 and get 1, 2 into 2 and get 1, 1 into 1. Then look what you've got here. 11 times 10 times 9 times 8, and it will go all the way to 4, which is exactly what we did over there. So that means it's exactly the same thing, and that is why this formula works so well. Okay, I'm just going to pause. I'll unpause the video just now, but just pause for a second. Right, so hopefully that seemed like no time passed for you guys. Right, so the whole idea just is that this permutation then makes my work a lot less, because I can use this formula. But again, like I explained to you, you don't need to know what permutation means. I just explained to you what permutation means so that you know why the calculator button works. You can just use the calculator button, and you can write it like that. You can say 11 permutation 8, type equal, and then get straight to that instead of having to manually do all of that. But I mean, if you worry you're going to get confused with the permutation, then rather do it manually. Okay, let's look at another example. Last little one. Oh, 2 actually. So the first one says, 9 runners run in a race. In how many ways can gold, silver, and bronze be allocated? So that means I have 9 runners available, so this is going to be my N. But I only want to allocate gold, silver, and bronze, which means I only want to allocate 3 spaces. I only want to choose 3 times. So it's not that it's that I only have 3 available to choose, it's that I only have 3 choices to make. So again, if you want to do it manually, you can say, first place, I have 9 people I can award first place to. Then once those 9 people, well, one of those 9 people has been awarded first place, I only have 8 available for the next one, which means I only have 7 available for the next one, and then I have to stop because I've run out of medals. So I could do it manually again like that, 9 times 8 times 7. There we go, 9 times 8 times 7, which is going to be 504. Or, like I said, if you want to, you can use the permutation, which in this case is going to be 9 permutation 3. So I'm choosing 3 out of a possible 9. And if I type that into my calculator, like I showed you, 9, shift, and then that multiplication button for permutation, you can see the P appears there. And then I'm going to press 3. It also gives me 504. So that's, again, a nice little shortcut to use. Okay, then the last example here. John has 6 friends he can invite to the movies out of 13. So John has 13 friends, but he only has space for 6 friends that he wants to invite to the movies. In how many ways can they be seated in the row at the cinema? So if you want to do this manually, you have to again go and realize there's 1, 2, 3, 4, 5, 6 places available in that row. Now, I know this one isn't very clear because technically speaking, you go and say, where does John sit? Let's say John is fixed over here. He's seated. So we're only looking at seating his 6 friends next to him. So he's there. So we're not worried about where John is sitting. We're just worried about those 6 friends that are sitting in a row. So obviously, because he has 13 friends available, we have 13 people we can put in the first seat, then 12, then 11, then 10, then 9, then 8. So you could do it like that. And you can go and type it into your calculator. There you go, 13, 12, 11, 10, 9, 8. So that's going to be equal to 1,235,520. Yes, a big number, but it's actually accurate. Or I can simply go and say, I have 13 people available, but I'm only going to choose 6. So 13 permutation 6. And if I type that into my calculator, 13 permutation 6, again I get the exact same value. So I can write down that 1,235,520. Right, so that is the content I wanted to discuss with you guys today. There will be some work to do on this some practice before we move on to the more complicated examples. Thank you so much for listening.